We're up to lecture number 7 in our Modern Marvels series. And our speaker tonight is Professor Michael Celia, having read in his CV that his interests and expertise include groundwater hydrology and water-stressed ecosystems. We might ask him to advise us on some of our Princeton basements. Professor Celia's undergraduate work was at Lafayette College, and his graduate degrees, 3 of them, are from Princeton. He is Theodore Shelton Pitney Professor of Environmental Studies, Professor of Civil and Environmental Engineering, and Chair of the Department of Civil and Environmental Engineering in Princeton School of Engineering. He's going to talk with us tonight about his work with large-scale projects that are addressing the critical problem of carbon in the atmosphere. This work is part of a large, multi-purpose effort at Princeton known as the Carbon Mitigation Initiative. His subject tonight is carbon mitigation. Mike?
Thank you. Well, thank you, everyone. It's a pleasure to be here. I am a little bit tired, but I think we'll get through the lecture okay. The title here is a bit more specific. What I'd like to do is to talk about the idea of geological storage of CO2, and this is part of a strategy that we usually refer to as carbon capture and storage, or CCS. And it is, at the moment, the only viable technology that would allow us to both continue to allow coal to be used in the energy economy, which for us means about 50% of our electricity production, which is from coal, and do something about the carbon problem. So that's why CCS is interesting. The work that I'll tell you about has been done largely as part of this CMI, which is the Carbon Mitigation Initiative at Princeton, which I'll say a few words about as well. Here's what I'd like to do during this evening is I'll give you a very quick overview of the CMI activities at Princeton, which you may have heard about from other speakers, and also an overview of the carbon problem, which may also be repetitive, but I think the numbers that I will give you, which are pretty simple numbers, are worth hearing a second time if you already heard them one time. Because it's helpful to know something about sort of the magnitude of the problem we're talking about. Then I'll say a few words about solutions that can work, feasible technologies that exist today, and how carbon capture and storage fits into that portfolio of options. And then we'll really focus on the geological storage idea. I'll say a little bit about what the subsurface is made of, if you don't know what's underground, a little bit about CO2 as a material, and then a few things about what happens if you take CO2, compress it, inject it into a deep well, and push it back into the ground, more or less where you took the carbon from. And the way that it works, and the things that we may need to be worried about or thinking about when we do that activity. All right? And in the context of all that, I will try to let you know some of the specific things that we work on here in my group and in my department, and also in the CMI, without going into any of the mathematical details, which I assume most of you wouldn't want to see. If you do, I'll be happy to show them to you. Well, CMI project at Princeton is somewhat unusual for this university. I believe it's probably still the largest industrial-funded project in the history of the university. It is funded jointly by BP and Ford Motor Company. It was initially a 10-year project. It's now been renewed for another 5 years. We're in year 9 of the first 10. The idea was to put together a broad group that largely addressed these 4 very big issues related to carbon. There's carbon capture, there's carbon science, of which there is much activity on this campus and at the Geophysical Fluid Dynamics Lab, GFDL, which is just up Route 1 on the Forrestal campus. Carbon policy and economics, and carbon storage. My part has been the storage part, and that's what I will tell you about tonight, but the idea of the CMI is that you really can't deal with this problem with only one of the boxes up there, or even only two of the boxes. That there are so many aspects to trying to solve the carbon problem that you really need to put together these sort of large multidisciplinary groups, and that's what we managed to do here at Princeton. So this is a curve that I'm sure you've all seen at some point. It's called the Keeling curve, named after the person who began to make these measurements of atmospheric CO2 concentration at the Mauna Loa Observatory in Hawaii. And what you see here is this sort of steady increase of CO2 from the mid-century 1950s up through the early 2000s. Passing through the 380s here, we're now sort of up well into the 380s. This curve is the simple manifestation of the carbon problem, and I'll make it more clear on the next slide. But I'll just make a comment that you see this average continues to go up with some wobbles around depending on a whole variety of things. You see these seasonal oscillations on top, growing season in the northern hemisphere, and the winter season when you don't have growth, which corresponds to uptake of CO2 and then not uptake of CO2 from vegetation. So vegetation plays a noticeable role in terms of the oscillations, but the clear upward trend is unmistakable, and there's no doubt that this is from anthropogenic emissions. No one will doubt that, even the ultimate skeptics. This is a little longer time scale. This goes over the last 1,000 years. So this is going back from 1,000 up to 2,000. This is data based on ice cores. So you can go core through old ice, and the trapped gas in there will tell you what the atmosphere was like at the time the ice was deposited. And what you see is that coming out of the last ice age, which is many thousands of years, or several thousand years in the past, the atmosphere stabilized at about 280 parts per million, micrograms per liter, parts per million. And it stayed that way until the Industrial Revolution, in which case we see this exponential increase in atmospheric CO2 to the current level of about 385 parts per million. Now, it's useful to put this into a context in terms of, so one number to remember is 280. That's what we usually think of as the background CO2, because that's what was stable for thousands of years before the Industrial Revolution. The second number to remember is 385, which is the current level of atmospheric CO2 concentration. All right? You can put this into a longer context, which is now about 1 million years, based on ice cores. And what you see if you look at the last 1 million years is 100,000-year cycles that are glacial, interglacial periods on the globe, meaning ice-covered, not ice-covered, okay? And they correspond to maxima and minima for CO2 levels. What you observe in that record is that for every maximum that happened over the last million years or so, none of them exceeds 300 parts per million. Okay, and the minimum is about 170. So we can correctly say that we are collectively, as humans, doing a global scale experiment where we are raising the level of atmospheric CO2 well beyond anything we've seen for at least 1 million years on the planet. Okay? And we are going to simply observe how the Earth system responds to that increase in a greenhouse gas. Okay? Now, the second thing I would say is that clearly, if we don't do something about our emissions, this exponential growth will simply continue, probably well into the many hundreds, probably approaching 1,000 parts per million. Okay? With that in mind, I would say it's reasonable to assume that at some point we will collectively decide that we want to stop doing this experiment. All right? And that's where engineering comes in. Because as engineers, we want to be able to answer the question, when the policymakers come forward and decide to actually do something meaningful, and say, what are the options to stop this exponential growth of CO2 emissions without collapsing our economy? We would like to have answers to that question. Okay? So that's the engineering part. It presupposes that the solution to this problem is a technical solution. Of course, it's prerequisite that we have a political solution. But the political solution doesn't mean anything if you can't do something technically to fix the problem. So those are the things that we work on in the Carbon Mitigation Initiative, are practical solutions for the carbon problem. And that means engineering. All right, good. Well, if you want to fix the problem, it's helpful to know where the CO2 comes from. So here's a pie chart from the International Energy Agency, IEA, showing globally the sources of CO2 emissions from fossil fuel burning, you see the largest sector of this pie is electricity generation, about 40%. All right? Second largest is transportation, about 20%. If you looked at a similar pie chart for the United States, you would see about 40% electricity, a little more than 30% from transportation. We drive a lot more than the rest of the world. Okay? But nonetheless, the two biggest slices are electricity and transportation, with electricity being the dominant one. So therefore, I would hypothesize that if you can't decarbonize the power grid, you can't solve the carbon problem, because it's the biggest slice of the pie. If you can't deal with the biggest slice of the pie, probably you're not going to solve the problem overall. So let's say we take that as a reasonable statement. It's an interesting thought experiment to think about what you would do with the rest of this pie if you had decarbonized power delivered to you. Electricity that didn't produce CO2 emissions. Okay? I would say that clearly we would then think about electrification of the transportation sector as opposed to using hydrogen or other kinds of fuels. That would give you another 20% of the pie globally, 30% in the country. Think about how you design buildings differently if you were delivered carbon-free electricity. Think of how you do everything differently if the electricity were carbon-free. If you go down, I think, that thought process, you get to solutions that can get a pretty good chunk of this pie taken care of, all presupposing that we can decarbonize the power grid. Okay? So therefore, decarbonized power becomes the focus of what we want to do. Some other numbers to think about. The current global emissions are, I don't know what they are currently, but the most recent estimate, which is just a year or two ago, is about 30 gigatons of CO2 per year. A gigaton is 10 to the 9, meaning a billion metric tons. A metric ton is 1,000 kilograms. Okay, so that's what a gigaton is, and we'll be talking about gigatons and megatons. So billion tons and million tons, 10 to the 6 and 10 to the 9, okay? And given the molecular weights of carbon and oxygen, this distills down to about 8 gigatons of carbon per year. Okay, O2 giving you an extra sort of 44 over 12 factor here to go from CO2 down to carbon, okay? I will use both these numbers in the next couple of slides. Projected emissions over the next 50 years, under most business as usual scenarios, the assumption is that the emission rate will go up by about a factor of 2. It's what is typically referred to as background doubling. Okay, so if we do nothing except some of the things we're doing now, the emissions rate will probably double in the next 50 years. Okay, we take that as background doubling. Well, one of the things that came out of this CMI activity was an idea of stabilization wedges, which some of you must have heard something about wedges, but let me give you a quick explanation. Here's a graph, again, of time on this axis going over about 150 years. This is now emission rate, okay? So at the moment, we're sitting here at 30 gigatons of CO2 per year, which is 8 gigatons of carbon per year. It's the same. The last 50 years, we increased by about a factor of 5. The idea is that the next 50 years, if we don't do much, we'll increase by about a factor of 2. That's this trajectory here, which gets us up to 16 gigatons of carbon or 60 gigatons of CO2, right? The doubling of the current rate. Now, one of the things that happens with groups like the IPCC that look at many aspects of the carbon and climate systems is that they make future projections about different scenarios and what the emissions would look like and how those emissions then feed back into how the climate might react, all right? One of the things that, one of the scenarios that is sometimes talked about is called the flat path scenario. It's exactly what it says, is that you keep emissions flat at the current rate over the next 50 years. That's a flat path. If you do that and then become more aggressive after 50 years, the models say that the delta T, the average increase in temperature, will be about 3 degrees C. Now, many people like to think of 2 degrees C as the limit for dangerous climate change. So this says that this is not aggressive enough if you want to live in a delta T of 2 degrees. But we'll see in the next slide that this is difficult enough, so let's just worry about trying to do this, all right? What it means is that instead of following this path, we follow this path. That means all the emissions corresponding to this green triangle have to somehow be avoided, right? If you want to go from one line to the other. So what my colleagues Steve Pacala and Rob Sokolow, both from here at Princeton, who are the principal investigators of the overall CMI project did was to say, look, let's take this triangle here and break it up into slices, that each slice increases over 50 years, so that after 50 years, the increase is 1 gigaton of carbon per year. And we call that a stabilization wedge. And this means if you want to get rid of the green triangle, you need technologies that will give you 8 wedges of emission avoidance. All right? Each wedge, by the way, corresponds to an emission, or an avoidance of emissions, totaling 25 gigatons of carbon over 50 years. It's just the area of one of the triangles. Okay? So then once you have this sort of this metric, okay, this measure, then you can ask yourself, what technologies will give me 1 wedge? Okay, and if you can get 8 of them, then you at least have some hope that you can solve the problem. All right? Well, here are a few things. This is an incomplete list. If you increase the fuel efficiency of 2 billion cars from 30 miles per gallon to 60 miles per gallon, I think at the moment there are maybe 700 million cars on the planet or something like that. So we don't even have 2 billion cars, but if in 50 years we did have 2 billion cars, they'd have to be much more efficient than they are today. If you like nuclear, take the current installed capacity globally, add twice that amount to it. That will give you 1 wedge. Think about the politics of doing that over a 50-year time scale. And even if you're the most pro-nuclear person, I think you would conclude that you wouldn't get more than 1 wedge out of nuclear. That's what I think. All right? Other things you can see here, you can look at whatever you want to look at. This is what I want to talk about today. You install carbon capture and storage, which I'll explain in the next slide, at 800 large-scale coal-fired power plants. If you do that, you get 1 wedge. All right? And as I said at the beginning, the reason I'm interested in this is a quote here from a report that came out of MIT from a conference a couple of years ago. It says, we conclude that carbon capture and storage is the critical enabling technology that would reduce CO2 emissions significantly while also allowing us to continue to use coal. And what it doesn't say here is that it's essentially the only technology that exists right now that would allow us to do that. There's a whole other sort of conversation we could have about whether or not we should reasonably expect the US or China or other countries not to use coal. Okay, I would say that it's almost impossible to imagine that that would happen. Maybe I'll be wrong, okay, but it's cheap, it's abundant, and you have energy security, right? We don't have to go to war in the Middle East to get coal. We just have to go to Appalachia or out to Wyoming or other parts of the country, and it's the same with China. And no one is going to walk away from a cheap, secure, abundant source of energy, I don't think. So we're going to continue to use coal. The question is, what will the emissions profile look like as we use the coal? All right. So carbon capture and storage is actually very simple. The idea is that we continue to use fossil fuels to power the electricity sector. Now, if you're in Greenpeace or maybe an even more radical group, you will typically stop me here and say, this is a bad solution. Because any solution that allows us to continue to use fossil fuels is a bad solution. Okay. I think that's a completely impractical point of view, and at the end of the day, not very helpful. But nonetheless, I get those debates all the time. The idea is that we continue to use oil, gas, or coal in the power facility. The way you design this is a separate talk, but you either retrofit old ones, which is not very efficient, or you just design your plant differently so you get a concentrated stream of CO2. One way or another, you capture the CO2 in a separate facility before you allow it to escape into the atmosphere. All right? And this is done by some chemical engineering processes. You then take the captured carbon and put it somewhere other than the atmosphere. That's the whole idea. And that means you either inject it into the oceans, which is politically difficult at the moment, and technically may not be the best thing to do, or you inject it into deep geological formations, more or less where you took the original hydrocarbon to power your system. This is what we're going to talk about today, the idea that you can inject this into deep geological formations with the purpose of keeping it out of the atmosphere for at least a time scale that allows you to solve the climate problem, which means about 1,000 years. All right? And you can put it into various kinds of formations, deep underground formations that are just filled up with salty water, called saline aquifers. depleted oil and gas reservoirs where we've already taken the hydrocarbon out, either with or without what's called enhanced oil recovery. So CO2 is sometimes injected into old oil reservoirs to stimulate more of the oil into the producing wells. All right, it's called enhanced oil recovery. You can do it with that or without that. And that's the basic idea. It's really not particularly complicated to understand. Let's look at some numbers. My best guess is that the current number of coal-fired power plants, sort of reasonably sized, is in the low 2000s across the globe right now. So if we were to magically retrofit, 2,000 and some old coal plants to have CCS, how many wedges would we get? 1, 2, do I hear 3? We'll have an auction. Well, you need 800 for one, so yeah, it's pretty close to 3 actually, right? So if you could make it happen, you get 3 wedges. Suddenly I'm interested, right? Because if you have a technology, that you really like, but it only gives you a small fraction of 1 wedge, then with all due respect, you're wasting your time. Because if you don't get at least 8 wedges at the end of the day, you can't solve the problem. All right? And by the way, one of the things I should have pointed out on the wedges slide is that you learn 2 things about this from this wedge analysis. One is that there are a number of technologies that exist that can solve the problem, but every one of them requires an enormous effort. You retrofit 800 large-scale coal-fired power plants. You're talking about an enormous effort to get you 1 wedge. The second thing you realize is that there's not a single technology that can give you all 8 wedges. So you have to be thinking about portfolios of technologies to solve the problem. Otherwise, you're not going to get where you want to be. Okay? The problem is big, and you have to have diversity of approaches. Those 2 things are both necessary if you want to try to solve this problem. All right. Let's see. China's been building coal plants like mad for the last number of years. 1 to 2 per week. I thought that was a wrong number, but it turns out to be a right number. Now, some of these are to replace old, really bad plants because of local air pollution problems, but some of them are new. But anyway, if you run these numbers, you see that you can get several wedges out of this if you decided to do it full scale. All right. All projections made by economists and others tend to have the CCS as part of the portfolio, so it's helpful if we understand how this works, and that's what I'm going to do for the rest of the talk. Well, the basic idea is pretty simple. We put it into the underground environment by drilling wells and pumping the fluid down instead of extracting fluid out, like some of you might do for your groundwater water supply at your home. That's a shallow well. These are deep wells where you go into the domain of oil and gas. Some of the estimates in terms of capacity, so how much could we actually put into these different parts of the underground, are relatively big numbers, okay, with the largest numbers being in deep saline aquifers. Okay, now remember, this is, let's say, some thousands of gigatons of CO2. That should be CO2, sorry, not just CO. The current emission rate in gigatons of carbon was about 30 gigatons per year. All right, so if you think about 3,000 gigatons capacity, that could take 100 years worth of emissions at the current rate. Okay, so CCS can get us across a kind of century time scale until we have some better alternatives to replace traditional fossil fuels. That's the way to think about this technology. It's not something that's going to continue infinitely into the future. It's a long enough bridge to think we can do something reasonable, and the technology is here that we can deal with it. Okay. Turns out that we already pull a lot of fluid out of the subsurface in the oil and gas industry, and we also inject a lot of fluid. But I thought I would tell you about a couple of things. One is that if you're going to know anything about carbon capture and storage, you should know about this particular project, often called the Sleipner Project, because the name of the platform in the North Sea is the Sleipner Platform. All right? Now, the story of Sleipner, and I'm not going to get through all my slides, but I'll just keep telling you stories because they're interesting to me. Here's an image of the Sleipner platform. This is a project that's run by Statoil, which is one of the 2 Norwegian oil companies, which have now merged into one big oil company, as oil companies are wont to do. In 1996, Statoil was producing from the Sleipner Formation natural gas on this platform in the North Sea. Now, the natural gas had a content of CO2 that was too high for them to put the gas to market. So they had to have a facility on the platform that would separate the CO2 from the methane. Okay? They put the methane to market, make a lot of money. They would normally simply vent the CO2 into the atmosphere. Norway in the early 90s imposed a tax on CO2 emissions. It's a very interesting tax. It only applies offshore, right? Which means they only tax oil companies. All right? But the tax at the time was close to $40 a ton of emissions. And Statoil realized that they could drill a well into a different formation. In this case, it's a formation called the Utsira Formation. Take the CO2 they've already separated and put it back underground, and it would cost them a lot less than the tax would cost them. So they decided to do it. It had nothing to do with science. It had nothing to do with climate. It had nothing to do with anything except they were going to maximize their profit, which is what they're supposed to do. All right? So that's what they did, and they started injecting in 1996, and they've been injecting since 1996 about 1 million tons of CO2 per year. And that is the first industrial scale injection of CO2 into the ground simply for the purpose of emission avoidance. All right? Other things that go on these days, and I'll show you a map in 2 slides for where some of these are involved. Acid gas injection, especially in Western Canada. Acid gas, sometimes you produce natural gas that has not only CO2 in it, but also H2S. And both of those have to be stripped out of the gas before you can put it to market. So that's referred to as a sour gas. And the mix of CO2 and H2S is referred to as an acid gas. Now, in the old days, that would simply be vented. But now in Alberta and in all of Western Canada, there are regulations on the emissions of H2S. Not CO2, but H2S. So therefore, what used to happen is that the H2S and the CO2 would be separated, the H2S would be processed into elemental sulfur, and you'd sell the sulfur to make some money. But there was so much sulfur being produced that the sulfur market collapsed about 15 years ago. So for example, I have flown over Western Canada and looked out the window. My geology friend was next to me, and he said, "You see that down there? And from 35,000 feet, you can see this big yellow brick sitting on the ground. And that's a bunch of elemental sulfur that somebody can't sell." Right? So it's enormous quantities that sit there, which are themselves an environmental problem. So now what happens is that this mix of CO2 and H2S is simply injected back into the ground. Okay, that's acid gas injection. Oil field waste, if you don't know, the largest disposal procedure for getting rid of liquid hazardous waste in this country is to inject hazardous waste underground into deep formations. A lot of that happens along the Gulf Coast, in the Mid-East, Michigan, a place like that, etc. The second place where there's CO2 being injected for the purpose of emission avoidance is in the desert of Algeria. It's called the Insala project. It came online about 3 years ago. Also injects about 1 million tons a year. This one is not for tax purposes. This is a field that's run in part by BP, and I would guess that BP, given that they are beyond petroleum, as you know, and have nice green and yellow logos, wouldn't want to be seen as emitting 1 million tons of CO2 into the atmosphere, so they are injecting it underground. And the nice thing is that they have put together a science advisory board to think about how we can learn from the activities that they're doing, and trying to be as transparent as they can, given that they have multinational agreements with other oil companies. And I sit on the science advisory board for this project, and it tends to be quite complicated to navigate all of the different players that are involved, but it's quite interesting, actually. Anyway, here's a map that was produced from a special report by the IPCC on carbon capture and storage in 1995. This shows all the activities related to CO2 and CO2 injection around the world. Looks impressive. Looks like there's lots of activity going on. Turns out that many of these things are very small-scale activities. The 2 I just told you about are here. Okay, this is Sleipner in the North Sea. Can you see the countries there? I guess so. No, not very well. Okay, but anyway, this is Norway up here, and this is the North Sea. And here's Insala in Algeria. The other 2 I mentioned were acid gas in Alberta, which is up here, and in West Texas, there's a lot of enhanced oil recovery that's done with the injection of CO2. Now, the interesting thing about West Texas is that the CO2 that gets injected is not captured from any anthropogenic emissions. It's actually taken out of the ground from reservoirs that would otherwise keep the CO2 underground. Okay, but Kinder Morgan and others will drill wells, pump the CO2 out of the ground, build a pipeline from New Mexico to Texas, pipe the natural CO2 down to get injected instead of simply capturing anthropogenic CO2. But that's the way it evolved. That's the way the industry evolved. Okay. If you look at the numbers, what you find is that here's the, I didn't mention Weyburn. I don't really want to say anything about Weyburn. It's an enhanced oil recovery operation. Here's Insala and Sleipner, each of them injecting about 3,000 tons of CO2 per day. And you find that a single sort of medium-sized coal plant will emit about 8,000 tons per day. So the sum total of these two doesn't add up to even the emissions of a single coal-fired power plant. So while it looks like there's lots of activity going on globally, okay, the sum total of everything doesn't add up to the output of a single power plant. It's close, but it's not quite. Here's a graph that shows these three major ones. Sleipner, 1 million tons a year. Weyburn came on. Insala came on. All three of these together, this would be the emissions starting in 90 or starting earlier from a coal-fired power plant. And you see that it's on the order of one plant. We need 800 of these things to get a single wedge. Okay, so I'll keep telling you for the next few minutes until I'm done. This is a very big problem. And if you're going to try to solve it by dabbling around the edges, you're just wasting everybody's time. Either you try and solve it at the right scale, or you're never going to solve it. All right? So you should think about strategies of how you can solve it. Well, where do we find formations into which we can do injections? Here's a map, again, from this IPCC report that shows the darkest indicate the best places to do injection. If you just look at North America, you see that the mid-continent basin here has lots of potential sites. All right? And that's pretty much where we look in North America. The North Sea is up there as well and various other places, but let's just think about North America for the moment. There's a lot of capacity in North America, it turns out. Now, before I go on, I wanted to say a little bit about what happens when you look at the subsurface, and I wanted to do it with two different maps. This one is an old study, which I took because it's local to the region. Here's Philadelphia, and here's Atlantic City. All right? And this is showing you what the geology looks like when you go across southern New Jersey. And what you see is a layered structure here of clays and sands and clays and sands and clays and sands. What I want to just point out is that the layered nature of this, where you have sands and clays that tend to be in alternating layers. Sand tends to be permeable, clay tends to be relatively impermeable. And that's the way that these materials tend to get laid down geologically. All right? The other thing to recognize is that even though this looks like a big slope here, the scale here is 250 feet in the vertical and 8 miles in the horizontal. So it's a very exaggerated vertical scale. And anytime you see these geological cross-sections, they're almost always very big exaggeration in the vertical. So don't be misled by the distortion. Now, here's a schematic on a much bigger scale of the Great Plains. And the two things I want to point out here are, again, the layered structure. So here are zones that are permeable, impermeable, permeable, impermeable, etc. And the second is that the blue is meant to indicate fresh water, and the gray is meant to indicate salty water. As you go deeper, you go from freshwater zones, where we tend to get our water resources from, into zones that have salty water, which is not of much use from a human perspective. Okay? It's into these salty formations that we think about injecting the CO2. Good. Go back to this map, which I just showed you. This is a map that shows the density of oil and gas wells. And what I want to point out is in North America in particular, the places where we saw were the best prospects for putting CO2 happen to also be the places where you tend to find oil and gas. Okay, so this is the density of oil and gas wells. In North America, there are probably 6 or 7 million oil and gas wells. All right? And I'll get back to that idea in a minute. But these mid-continent sedimentary basins, we know a lot about them because we produce a lot of oil and gas out of these formations. And these are the places where we think about putting CO2. Okay, I want to say a little something about CO2, and then I'll say a few words about what happens when we inject it. This is called a phase diagram. It's temperature on the x-axis and pressure on the y-axis. And what it says is that at different combinations of pressure and temperature, CO2 will take on different phases, liquid, solid, gas. Okay? So you can see what's gas, what's liquid, etc. So under normal room conditions, CO2 is a gas. Density of about 1.8 kilograms per cubic meter. Okay, it's a little bit denser than air. But the other thing you see on here is something called a critical point. This guy right here, okay, which is at about 31 degrees and about 7.5 megapascal, if that means anything to you. But the point is, if you go to high enough temperature and pressure, the CO2 becomes what's called supercritical. It means beyond the critical point. All right? And here you wind up with densities of about, let's say, on average, maybe 500 kilograms per cubic meter, right, instead of 1.8, with viscosities that are still relatively low. Almost all of the injections that are talked about with carbon capture and storage will involve supercritical CO2. Okay, and supercritical just means beyond the critical point. It means you're going deep enough that it becomes hot and under high pressure. And that's where we're going to inject the CO2. It has a high enough density that it looks attractive, and that's what it means. And what it means is that the depth would typically be about 800 meters and deeper for where we do the injection. So we're talking about injecting 1 kilometer, 2 kilometers, 3 kilometers below the land surface. That's pretty deep. All right? When am I supposed to stop, by the way? Nobody told me. 20 minutes, okay. Or if everyone gets up and leaves, then I know I should stop as well. Okay. This is the most technical slide I have, I think. And it says a little bit about what happens if we inject CO2 into one of these deep, salty, water-filled formations. All right. So the injected supercritical CO2, slightly miscible with the brine. What it means is that if I put the CO2, just separate CO2, next to salty water, a little bit of the CO2 will dissolve into the water, a few percent. The rest of it stays as a separate phase, just like oil and water. Okay, so they don't really mix, but a little bit will dissolve. Now, that turns out to be important in the long term, because if you wait long enough, you know, a little bit dissolving everywhere means you can dissolve a lot. Okay, so the ultimate fate of the CO2 will be that it will dissolve into the water that's down there and sort of move with the water system. So we need to think about that. It's always less dense than the brine. I said it goes up to 500 kilograms per cubic meter. Well, the brine might be 1,200 kilograms per cubic meter. Okay, so while the CO2 is fairly dense, it's still much less dense than the brine. So when I inject it, buoyancy will tend to push the CO2 up because it's less dense. Okay? We need to think about that. Less viscous and water can evaporate, etc., and we can write a bunch of equations that I'm not going to write here. But the idea is that, I mean, everybody should understand that you know, you take a sample of rock, okay? Hard rock, a sandstone. Okay, you get sandstone coasters, for example. They have nice patterns in them and all those sorts of things. But a sandstone is a solid rock that has a pore space in between the solids. Maybe 20% of the total volume is not solid. Okay? It's that pore space that's filled up with the fluids. And that's where things exist. Take a sand pile, is unconsolidated, okay, but still has pore space in between, and water and other fluids move. That's where all the groundwater comes from. Okay? When you go deep, you get these consolidated rocks, but it's the same idea. And that's what this schematic is meant to indicate. That the green here is meant to indicate solids, and in between the solids, we have the void space. Some of it's filled with the brine, and some of it gets filled with the CO2 that we inject. Okay? And there's this interesting hydrodynamic go on in terms of how things move underground and all that sort of thing that I'm happy to tell you about, but only if you ask me. Because I'll start writing equations and then it'll be a big mess. Anyway, so here's what we can think about in terms of one of these injection operations, is that let's say you put a well down here, okay, and I inject CO2. I'm going to forget this line here, but what happens to the CO2? I know that it's less dense than the brine that's in here. So you pressurize the CO2, it pushes a bunch of the brine out of the void space further away from the well, and it occupies the space with CO2. It will, because it's less dense, it will tend to move upward, all right, in what's called, what the petroleum engineers call gravity override. Okay, it's descriptive, right? Gravity being buoyancy, override meaning it goes over top. It'll continue going straight up to the surface unless I have some formation above here that's impermeable. That's where the layered nature that I showed you before is important. I inject into the permeable layers, and it should be overlain by an impermeable layer. The geologists and the petroleum guys call that a cap rock. It's the rock that caps the formation. All right? You need two things to do this injection. A formation that's permeable enough to take enough CO2 to make it worth your while, and a formation above it that's impermeable enough to keep the stuff down there. And if you have those two, then you win the game. Okay, you've got a good site. And this is what will happen. Okay, so as long as you have that, everything is good. I want to think about, if we do this operation, what's going to happen? I inject the CO2. It stays as this sort of separate fluid, right, like oil and water not mixing, with only a little bit of it dissolving. As long as it's a separate fluid, it has a buoyant drive pushing it up, and if it encounters any imperfections in this cap rock, it could leak out of the formation upward into groundwater zones, to the land surface. If too much gets to the surface and goes to the atmosphere, you're just wasting your time, okay, and wasting your money, so you need to worry about that. But this is this idea of two separate phases, meaning two separate fluid phases, one aqueous, brine, and the other CO2, all right? Most of the CO2, to start with, meaning during the injection phase, which is sort of the lifetime of a power plant, 50 years, for example, will remain as a buoyant separate phase fluid. If you wait long enough, a significant amount of it will dissolve. I already told you a little bit dissolves. If you wait long enough, it diffuses away and more dissolves and more dissolves. And you can get some geochemistry going on at later times. But these sorts of processes happen more or less sequentially, all right? And what we know is that the only one of these that really has any risk of leakage is when you have this early time buoyant fluid that will move up naturally, all right? So that's where we think about risk. But in this case, this is again from this IPCC report. I don't know if this is, the light has gone off, so the battery's probably gone off too, but you can probably hear me without this. Yeah, that's fine. Anyway, the idea of storage security is that as time goes on, all of the physics that happen to the CO2, it'll dissolve, it'll become trapped by capillary forces, all of these things make the storage more secure. So as time goes on, the system behaves better in terms of any sort of environmental risk. So let me tell you just show you a quick result of some of the analysis that we like to do. Here again is the Sleipner platform off the southern coast of Norway into the North Sea. This is the entire formation into which the injection is happening. There are many things to say about that, but this again is the Sleipner is the Utsira formation. Norway is now planning to build two essentially zero-emission power plants along the coast. This is using natural gas as the fuel, but they will capture the CO2, and they will then pipe the CO2 out in the North Sea and inject it in formations under the North Sea. And in this case, for one of the plants, the formation here is called the Johanson formation, and we've been doing some studies to think about what will happen to the CO2 when it's injected into this formation under the North Sea. So this, for example, is a sort of a diagram of what this particular formation looks like. This is a fault zone where the actual formation splits in two because of various geological processes. There's lots of variability in terms of its slope and its topography and its parameters and all that sort of stuff. So we build computer models that will tell us what will happen to the CO2. So here's a case where CO2 was injected, and we sort of track it along. The injection point was here. We track it along to see what happens. And what I wanted to show you is one result here where, I don't know with the lights here, you can't see this very well, but let's just look at the outline of the black, all right? These black outlines here. After 100 years, this is the extent of this buoyant CO2, okay? After 200 years, it's here. After 400 years, it's here. And after 3,000 years, we just get these little pieces here, which get stuck under local dome structures in the cap rock bottom formation, all right? And the rest of it is either dissolved or trapped with capillary forces. And you can take all of this kind of detailed information and make your own version, or we make our own version, of that storage security diagram I showed you. So with time here, you see the white up at the top is the amount of this free phase CO2, this buoyant CO2. It very quickly, sort of on the scale of about 100 years, becomes essentially immobilized either by local capillarity, which I haven't explained to you, and I'm not going to bother because I don't have time, but this is the same reason that in an oil field, if you can get 50% of the oil out of the ground, you're doing very well. The rest of it gets stuck behind, and you just can't get it out because the small-scale forces keep it sort of in the rock, okay? Well, when you stop injecting and water comes in and sort of flushes out some of the CO2, it doesn't flush out all the CO2. The CO2 gets left behind in the same way that oil gets left behind, and that's this residual CO2 trapping. Some of it dissolves, as I said, here, and we can track all of these things and put quantitative measures on this sort of cartoon of storage security by simply looking at these different components here. And this is one of the things that we like to do, in part because regulators want to know what will happen. The EPA is now in charge of federal regulations and writing rules for these kinds of injections. And we not only have to look at short-term risk of leakage, which I'll show you an example of next, but we have to think about long-term fate and what's going to happen. And the long term becomes especially important when you think about liability issues, because if you think about this injection game, who's going to do the injection? Probably it's going to be the BPs, the Exxons, and the Halliburtons and the Schlumbergers of the world, all the ones that make a lot of money getting hydrocarbon out and more or less leading to the CO2 problem. They will now make even more money to fix the CO2 problem because that's their expertise. Okay? There's no point in getting upset about it. It's just the way it's going to be. Let's see. Now I have one of these things where I haven't slept for so long that I forget what I was going to say about them. But I hope it was something nicer than I inferred with my joke about them. Let's see. Of course. No, I remember what it was. Liability. They will not accept liability on a 1,000-year timescale. Okay? They will accept liability while they're doing the injection. Okay? So what does it mean? It means that think about a regulatory structure. You do the injection for 50 years, and then somebody, meaning the EPA, is going to stamp and say, okay, you've done a good job. You're going to say thank you very much. You're going to walk away with your money after the injection operation, and everybody in this room, or somebody is going to collect some kind of fund that will deal with liability issues in the sort of post-closure period. Okay? So the long-term fate of what happens to the system is important to understand liability risk and how much the public is going to collectively take on once the injection stops. Okay? So there are many reasons to think about this, but some of them are these sorts of liability and regulatory issues, which are very interesting. And right now, it's a remarkably interesting time because EPA has published proposed rules for CO2 injection wells, and right now it's in the middle of discussion period. So, okay. Well, this idea of leakage is one of the things that we look at in my group a lot is a possibility of what you might think of as unintended consequences. You try and solve the climate problem, and you try to now hope that you're not going to create a problem that's just as bad by doing something that you're going to regret in terms of the subsurface. And we're talking about injecting a lot of carbon into the underground system. And we'd like to feel somewhat confident that it's going to work. And the thing that we tend to worry about a lot is how much of these different fluids will leak, and what are the possibilities that it will simply diffuse through the cap rock. Okay. It's not really a leakage issue. There's an interesting technical part in terms of how it feeds back into pressure, but the first one of these bullets, from the point of view of leakage, is not very interesting. Faults and fractures are natural things that occur in rocks, and we need to worry about them, and fault zones are difficult to deal with. But the thing about North America that I've already told you is that we've got about 6 or 7 million old oil and gas wells, and they can act as leakage conduits, and it happens that they tend to be drilled in the same place where we would want to put the CO2. So, we can think about diffuse leakage in this diagram I showed you before. Leakage along faults and fractures can with the brine and the CO2. But I want to say a few words about wells, and just to get us thinking about some of the issues that we might want to deal with. We've been working a lot in Western Canada for various reasons, and And there's a location, lighting is a little tricky here, southwest of Edmonton, where there are 4 large coal-fired power plants, emitting collectively about 30 million tons of CO2 a year. And we thought that this area, which is highlighted here more or less, which is about 50 kilometers on the side, would be interesting to look at to see what would happen if we did an injection there, did a carbon capture and injection. So the first thing we did was to think about oil and gas wells. And if you look at this 50 kilometer by 50 kilometer area, you find that on this graph, each of these blue dots represents an existing oil or gas well. And if you add them up quickly, which I'm sure some of you can do, you get about 1,250 of them. Okay, so about 1,000 old oil and gas wells in the domain where you'd like to put your CO2. Now, what does a well do? A well will go through a cap rock because the cap rock keeps the oil and gas in place. But you want to get the oil and gas out of the ground. So you drill a hole in the cap rock, pull the fluid out. So now you've got a Swiss cheese of 1,250 holes in cap rocks that you have to think about whether or not that cap rock can keep the CO2 in place. It becomes a very interesting question, it turns out. So here, for example, is what the stratigraphy looks like. I'll just point out, I can't read it from here, that you have aquifers and aquitards, aquifer, aquitard. This aquifer means permeable, aquitard means impermeable. The layered structure I told you about again in the subsurface, all right? And if you look at those wells and project them in terms of depth, okay, onto a single cross-section, here's what all 1,250 of these wells look like. All of these indicated formations are possibilities for injecting CO2. All the blue here are permeable formations. The practical issue one of the practical issues that we need to think about is how much of this otherwise perfectly good pore space to use to inject CO2 are we going to simply walk away from because we think the risk of leakage is too high. If you have 1,000 wells going through the Viking, for example, has just about 1,000 wells going through its cap rock. Are you going to deal with that, or are you going to walk away and say the risk is too high? Okay, and it's a big issue in North America because it might mean that we walk away from 60% of our capacity to put the CO2 underground. All right? So we've been trying to do a bunch of risk analysis to understand how this is all going to work. And we think about the idea that you might inject CO2, you get a plume that spreads out, you might encounter some number of existing old wells, some of which might leak into other formations above, into drinking water zones, into unsaturated zone, into the atmosphere. What does it all mean? What should we worry about? What should we not worry about? I get phone calls from the insurance industry because insurance companies are thinking about how they're going to insure a CCS operation, and therefore this is all they think about. What's the risk? And if something happens, what's it going to cost me? Right? That's the insurance game. So there are many players getting involved here that ask practical questions about all of this sort of interesting dynamics that can happen, all of it underground. All right? Well, we have a whole program here trying to understand materials that wells are made out of, well cements. My colleague George Shearer does a lot of cement chemistry and trying to figure out what leakage might look like along a well. We've done a bunch of experiments. Our former student, Andrew Duguid, looked at how cement degrades under different conditions and a whole bunch of things like that. At the end of the day, what we try to do in my group is to think about how we can come up with probability distributions for what might happen in terms of leakage. So this, for example, is a plot. This is the logarithm here, log in base 10. So this is 10 to the minus 2. That's 0.01. 10 to the minus 3, 0.001. This is the fraction of the CO2 that we inject over 50 years, the fraction of that actually leaves the formation by leakage. All right? And we have a whole bunch of uncertainty in the input, so we get this broad distribution in terms of output. And these are the sorts of things we look at. So, here, for example, this is 1%, right? 0.01 is 1 out of 100. That's 1%. Under the conditions we looked at here, 25% of the time, we'll lose more than 1% of the CO2. Now, 1% in the conversations that happen with regulators and others is a kind of magic number. Some people use 1%, some use 0.1%. But DOE these days says that they want to have 99% of the CO2 remain underground for 1,000 years. Okay, that's their target, or at least that's what they want instrumentation to do. So this allows us to think about these sort of probabilistic risk profiles in ways that make sense to me. Okay, so anyway, I can give you a lot more details about that, but since time is up, what are we doing these days? In addition to what I said, we're continuing to develop a whole bunch of computational models. We work with BP and now also with Schlumberger through some DOE funding to actually re-enter old wells with logging tools and some experimental tools to try to understand what the materials are like after they've been in the ground for some decades, and what's the potential for leakage along these old wells. It's a very interesting program. It's expensive to do, but it's interesting nonetheless. We've got lots of work going on with Norwegians. We're developing a bunch of web-based tools because part of my funding these days comes from the Environmental Protection Agency. It's very interesting. I get funding from EPA and I get funding from BP. So when somebody, I've sometimes asked the question by environmentalists to say, is it true you take money from BP? I say, yes. Do you really think you can be objective? And then I just say, yes. And then they'll say, no, we don't think you can be objective. So then I say, well, I also take money from the EPA. So do you think I can't be objective on the other side as well? And I guess if I'm not objective on either side, then it leaves me being objective, right? Because anyway, we're trying to look at what happens at some of the interesting target bases. Illinois Basin in particular will, I'm quite sure, be the first place, if we ever do anything, where we'll see large-scale carbon capture and storage in a particular formation called the Mount Simon Formation, which can take a lot of CO2. And we have a project that's just starting looking at what will happen in Mount Simon in the Illinois Basin. Quite interesting, for me anyway. So the concluding remarks is to remind you that the magnitude of the problem is big. I would consider it to be a sort of environmental grand challenge for the early part of the 21st century at least. Remind you that CCS is the only viable technology that can allow us to use coal and deal with carbon at the same time. That we need to think about unintended consequences because, of course, history is full of good ideas that led to bad outcomes. So we'd like to try to avoid that if we can manage. And CCS is likely to be a central technology if we ever get serious about trying to solve the carbon problem. And if you're interested in some additional resources, I suggest if you just go to the IPCC website, you can easily download the special report on CCS. Very nicely written, especially Chapter 5. If you want to see some current research papers, there's a new journal called International Journal for Greenhouse Gas Technologies, which has some accessible papers that are relatively easy to read. Of course, if you want a bestseller that's going to be coming out soon, I'm writing a book with my good friend Jan Nordbatten from Norway. Chapter 1 is not mathematical of the book. And we're putting some websites together as well. If you're interested, I'll be happy to give you more information about it. Thanks so much for your attention. Yes?
Is there any estimate as to what fraction of the energy you would get from the well by drilling is required to put the CO2 separated and put it back down?
Yeah, so the energy penalty tends to be sort of 25% or 30%, something like that, with most of it coming from the separation, from the carbon capture. Okay, so what it means in terms of cost, see if we convert it into electricity bill. So if all of your electricity, well, it's a little bit tricky. Let's assume you took that all of your electricity, whatever electricity comes from a coal-fired source, which is not that much in New Jersey. If it all were converted overnight into carbon capture and storage with the extra cost associated, your bill would go up by about 6 cents per kilowatt hour. Now in New Jersey, we pay about 15 cents a kilowatt hour. So that means that if all of your electricity were to go CCS, the electricity bill would go up by about 30%. Now, that sounds like a big number, and everyone loves to use that number to tell you that it's so expensive we shouldn't do it. But think about the practical reality. You can't get to that point without probably 2 or 3 decades of development. You can't just overnight convert things, it doesn't work that way. So if you think about a 3-decade implementation, after 3 decades, the fraction of your bill that corresponds to coal would go up by, say, 30%. Okay, well, suddenly it looks like almost nothing on a per year basis relative to all the rest of the increased costs that we all face. So, I like to think about the cost involved as really not being a major factor, even though no one else ever says that. But that's how I think about it, because at the end of the day, you can go through an example of all sorts of other costs at the household level that you see. You would not notice this cost coming online. That said, the economics of this are the only thing that will allow it to work, which means that it has to be a top-down decision that the cost of emitting to the atmosphere is going to be high enough that all of the power companies will be incentivized to do something else. CCS being an option, maybe all the coal companies will go into solar. Maybe everyone will build wind farms, whatever. Okay, but it's all about economics at the end of the day. Yes?
Anything known about the pH of these brine layers?
Yeah, sure. Of course, you put CO2 down and the pH will decrease, and that is what drives the degradation of the well cements that I showed you. I didn't explain it, but I showed it to you. And it tends to be the concern about what happens. What happens if CO2 leaks into a fresh groundwater zone? The joke is, of course, that you have Perrier and you can sell it for a lot more than you would otherwise. The reality is that it will decrease the pH of the water. And that can drive a whole series of geochemical reactions, which is the concern about CO2 getting into the groundwater. Now, my own sense is, even though I'm not a geochemist, my own sense is that those concerns are sometimes exaggerated in the sense that what can happen? Okay, if you've got certain metals that are sorbed onto the solid and therefore of no real concern, you change the pH, you can essentially desorb the metals off the solid, mobilize them, and lead to a contamination problem that wouldn't be there otherwise. Okay, there aren't that many parts of the country where you would see high enough levels, and typically it's only arsenic that you would worry about in certain parts of the country in that regard. But nonetheless, I assume what you're implying with your question is that you need to worry about the pH, and in fact that's the main driver in terms of the response in the aqueous phase with the CO2 in it. And it's the acidified brines that drive a lot of the environmental concerns that come up. So, yeah. Yes?
Aren't there other greenhouse gases, like methane, that we have to be concerned with?
Sure. But CO2 right now still is the dominant anthropogenic greenhouse gas. So that is, and it's the one whose atmospheric signature is clearly continuing to go up exponentially. So it's the argument is analogous to my argument about the electricity sector. It's the biggest slice of the pie, and if we can't attack the biggest slice of the pie, then we can't eat the pie. Right? So that's, yeah. But yes, the methane, of course, is the second in the list of importance in terms of the overall effect. Methane itself, a molecule of methane, is a much stronger greenhouse gas than a molecule of CO2. But there's just so much more of the CO2 that it dominates the atmospheric greenhouse signature at the moment. Yes?
Wasn't there a problem quite a few years back with the injection wells causing small earthquakes?
Yeah, well, the most recent one was a geothermal well that in Switzerland. That was one where the purpose, this was to do some geothermal stimulation. That was a case where the well itself used what's called hydrofracking, which is that you will inject at a pressure that's high enough to create local fractures. All right, and the idea is that that increases the permeability of the rock and therefore gives you more access to the space. Okay, and fracturing of rocks is used in lots of different activities, including enhanced oil recovery to get better sweep and things like that. That caused a small, more or less, earthquake, which shut the entire project down. there have been similar things that happened with injections outside of Denver, which may be what you're thinking about. It's a concern, and people who do geomechanics will talk about this a fair amount. My answer to this is usually that there are many injection operations that go on all around the world, and in most places, including here and in Canada and other places, there are regulations that say, for example, that you can't have a pressure in your injection well that goes above, say, 80% of your estimated fracture pressure, specifically to avoid any kind of fracture, inducing fractures that can then lead to sort of microseismic events and those sorts of things. So there are regulations in place that are meant to minimize that risk, and they have to do with strict limits on the pressure that you can build up at the injection well. And I know of at least one, and probably two of those acid gas injection wells in Canada that have been shut down because the operator exceeded the allowable injection pressure at the injection well. So there are serious regulations, and that is usually what's put in place to try to control the issue of generating small-scale earthquakes, right? Yeah.
As large volumes of CO2 are injected, how much of the water is going to be displaced, not simply laterally, but also vertically?
Yeah. Well, whatever volume of CO2 goes in, that's the volume of water that will be displaced. More or less, well, it's true. We have argued for a while, and this is part of our conversation these days with the Environmental Protection Agency, that the movement of the displaced brine is probably equally important to the movement of the CO2, and may in fact be the thing that tends to contaminate groundwater sources more than the CO2. The reason is that the extent of a CO2 plume will be a certain distance. All right, the extent of the pressure perturbation that you build up tends to be much bigger, and it's this extra pressure in the formation that pushes all fluids up, down, out, whatever. All right. So there'll be a much larger volume of brine with an elevated pressure than there is just the CO2. So in all of the analysis that we do, we don't only look at how much CO2 leaves the formation. We always look at how much brine leaves the formation as well. All right. So we always track both of those fluids to see where they wind up going, and any risk analysis we do includes both of those. The other thing to remember, by the way, is that both the fluids and the rock have some compressibility. Even water has a little bit of compressibility. And in these systems that are aerially very extensive, large systems, the compressibility effects are noticeable in the sense that you get sort of finite propagation speeds of the pressure pulses, and so there is some compressibility in the system. It's not just a strict volume balance. Okay, but yes, the displaced brine has to go somewhere, and we want to make sure that we have some idea where it's going. That's for sure. Thanks for bringing that up. Yes?
Talk a little bit about where EPA is in their thinking about what you're thinking about.
Yeah. So EPA, it's interesting. They have a program which is called the Underground Injection Control Program, the UIC program. All right. That essentially came out of various additions to the Safe Drinking Water Act. Okay, so the Underground Injection Control Program is charged with protecting the subsurface water supply, groundwater, in the country. And so at the moment, the UIC has 5 different classes of wells, one of which is hazardous waste injection. All the hazardous waste injection is controlled by this UIC program, okay, hazardous waste injection well classification. EPA has now proposed a separate classification of well, a Class 6 well, which is strictly CO2 injection wells. All right? And they have put out 250 pages or something like that of the proposed regulation. The thing to know about that is that their view and their charge is to protect underground drinking water supplies, and therefore the entire view of the CO2 injection operation is from the point of view of protecting groundwater, not protecting the atmosphere or anything like that. It's a groundwater-centric view, and because that's the group that was charged to write these regulations. So that's what's happening at EPA. I'm quite sure that there will be a separate new class of wells, class 6, that will be CO2 injection wells. One of the things that will be required is, so right now, if you want to inject hazardous waste, all right, you have to do a study and say that it'll stay where you say it's going to stay. Okay. Now, what part of that study is you have to identify something called the area of review, which is the area around the well that you say potentially could be impacted by the injection. If you look at the rules for hazardous waste injection, you either define your own area of review or you use 2 miles as a default. Okay, so everybody uses 2 miles as a default. You go see what's happening in a 2-mile radius around your well and you do your analysis. I've seen these reports. I tried to read through one. It was literally 70 3-ring binders, sort of 5 inches wide, stuffed full of paper. And I said to the EPA guys, you can't seriously tell me. And they swore that they read every page. Okay, that would be like 100 years of work or something. But anyway, that's what they told me. And that's what comes out of these. The actual analysis is actually quite simple and not that long. Everything else is just a whole bunch of supporting stuff that I don't know why it's in there. But
Is there someplace else in EPA where it would be more appropriate?
I think this is perfectly okay, actually, because this is a group that thinks all the time about what happens in the subsurface. I'm pretty comfortable with them doing what they're doing. What I wanted to say about area of review, though, is that in the CO2 problem, EPA has recognized that they're not going to just put a default value for an area of review, so that the operator or the person putting in the request for a permit, putting in the application, is going to have to do an analysis to say what the area of review is and how it changes with time. So one of the things we're trying to do is that, when you try to analyze these systems, you use these computer simulation tools that are very complicated. They're used in the oil industry and they're used in various places. And what we're doing is to put together simplified tools so that the EPA field people can have some basis to make their own estimate for what the area of review should be, how big the plume is going to be, so that if an application comes in and it's an order of magnitude off, they at least have some idea where to start asking questions. All right, but these things are all going to have to be defined, and then EPA is going to have some way of evaluating whether or not what's being proposed makes sense. It'll be an interesting learning curve, I think, for the first 10 or 20 of these that come in. That's for sure.
Well, let's thank Professor Celia.
Thank you.